Hello everyone. In this video, we're going to discuss how we are going to sketch the graph of a given function. In here, we have a sample sketch of a graph, and this is actually the graph of the function y equals x minus 4 all over x squared minus 9. Now, this curve can be broken down into several components, namely intercepts, symmetry, asymptotes, critical points, points of inflection, and the behavior of the curve in each region. Now, these parameters will guide you in sketching the curve of a given function. Alright, so let's go over it one by one. First is the intercept. Intercepts are points of x and y axis where the graph of the function passes. So if we're going to look at the graph of the given function here, and we're going to locate the x-intercept and the y-intercept, here are their locations. Now, solving for the x-intercept of the given function, we're going to set y equals 0 and solve for the values of x. Similarly, if we are interested in determining the y-intercept, we're going to set x equal to 0 and solve for the values of y. And that's how you solve x and y intercept. Now, let's talk about symmetry. To understand symmetry in the graph of a function, let us take a look first at this image. When this image is flipped with respect to its vertical center, the resulting image is identical to the original image. Therefore, we can say that this image is symmetrical with respect to its vertical center. Graphs of a given function could be symmetrical with respect to the x-axis, or with respect to the y-axis, or with respect to the origin, or it could be symmetrical in all areas of the Cartesian plane. Now, let us discuss how to test for symmetry for the given function. The first test is to change y to negative y. If the equation is unchanged, then there is a symmetry with respect to the x-axis. And if there is a symmetry with respect to the x-axis, the graph of the function will look like this. Whatever you see above the x-axis is mirrored below the x-axis. The second test is to change x to negative x. If the equation is unchanged, then there is a symmetry with respect to the y-axis. And if there is a symmetry with respect to the y-axis, the graph of a function will look like this. Whatever you see on the left side of the y-axis is mirrored to the right side of the y-axis. And the last test is to change y to negative y and x to negative x simultaneously. If the equation is unchanged, then there is a symmetry with respect to the origin. And if there is a symmetry with respect to the origin, graph of the function will look like this. Whatever you see on the first quadrant is mirrored to the third quadrant, and whatever you see on the second quadrant is mirrored to the fourth quadrant. Now, if we're going back to our sample graph here, and we're going to test for the symmetry of the function y equals x minus 4 over x squared minus 9, the first test is to change y to negative y. If we're going to change y to negative y, the resulting equation would now be negative y equals x minus 4 all over x squared minus 9. And comparing the resulting equation to the given function, the equation was changed. Therefore, there is no symmetry with respect to the x-axis. The next test is to change x to negative x. And if we're going to change x to negative x, the equation would now be y equals negative x minus 4 all over negative x quantity squared minus 9. And simplifying this, we have y equals negative x minus 4 all over x squared minus 9. So if we're going to compare the resulting equation to the given function, the equation was changed. Therefore, there is no symmetry with respect to the y-axis. And for the last test, we're going to change both x and y to negative x and negative y simultaneously. So we have here negative y equals negative x minus 4 all over negative x squared minus 9. And if we're going to simplify this one, we have negative y equals negative x minus 4 all over x squared minus 9. So comparing the resulting equation to the given function, the equation was also changed. Therefore, we can say that the graph is not symmetrical with respect to the origin. So generally, the curve has no symmetry, and it is obvious on the appearance of the sample graph in this function. After testing for symmetry, we're now going to determine the asymptotes of the given function. An asymptote is a line or a curve that continually approaches a given curve but does not meet it at any finite distance. They are usually present on graphs of rational fractions. We have different types of asymptotes, and in these functions we have two vertical asymptotes and one horizontal asymptote. If the given function is not a rational fraction, you can omit this step. So how are we going to determine asymptotes of a given function if we have y equals f of x over g of x? In determining vertical asymptotes, equate the denominator g of x to 0, then solve for the values of x. In determining the horizontal asymptotes, we have three conditions in doing so. If the degree of f of x is less than the degree of g of x, the horizontal asymptote is the x-axis, or that is y equals 0. If the degree of f of x equals the degree of g of x, the horizontal asymptote is y equals the coefficient of the highest power of x in the numerator divided by the coefficient of the highest power of x in the denominator. And lastly, if the degree of f of x is greater than the degree of g of x, divide f of x by g of x to determine the oblique or curvilinear asymptote. Note that the curve may or may not cross HA or oblique or curvilinear asymptote. Now going back to our sample function here, solving for VA, we have x squared minus 9 equals 0, and x squared minus 9 can be factored out to quantity x minus 3 multiplied by quantity x plus 3. And solving for the values of x, we have x equals negative 3, x equals positive 3. Now, solving for the horizontal asymptote, if we're going to look at the given function, if the degree of f of x is less than the degree of g of x, the horizontal asymptote is the x-axis. The degree of f of x is less than the degree of g of x, or that is y equals 0. Notice here that the curve crosses the horizontal asymptote at x equals 4, which is also the x-intercept of the given function. Now, that is how you determine the vertical and horizontal asymptote of a given rational fraction. The next step here is to determine the critical points. And to do that, we're going to solve for y prime, set y prime to 0, solve for the values of x, and locate the y coordinates of the critical points. Now in this graph of the sample function, the minimum point is located here, and the maximum point is located here. After locating and classifying the critical points, we're now going to locate the points of inflection. And to do that, we're going to solve for the second derivative of the given function, set it to 0, solve for the values of x, and then solve for the y-coordinates of the points of inflection. And in this graph of the given function, the point of inflection is located here. After locating the points of inflection, we are now going to determine the behavior of the graph in each region. For rational fractions, the number of regions depends on the number of vertical asymptotes and x-intercepts. However, if the function is not a fraction, the number of regions depends on the number of x-intercepts. So for this given function, since we have two vertical asymptotes and one x-intercept, we're going to consider four regions here. The leftmost region is the region where x is less than -3. The next region from the left is the region where x is in between -3 and +3. The third region from the left is the region where x is greater than 3 but less than 4. And the last region from the left is the region where x is greater than 4. So in this final step, our objective is to determine the behavior of the curve in each region, whether it lies above or below the x-axis. And we can do that by substituting any value of x that lies in a particular region. Now that we know the steps, we can now trace the curve of a given polynomial function.